I 3D printed a mini wind turbine. It lights an LED when you spin it. Let's understand how it works and what it took to build it. The generator that lights the LED is a brushed DC motor. This DC motor has permanent magnets in the stator, which is the outer part that doesn't move. In the rotor, which is the part that rotates, there are a lot of windings wound around the armature, which are connected to the commutator. The brushes, which brush against the commutator, are stationary, and that's where we connect to. As the rotor spins, there's a changing magnetic field passing through the windings. Let's imagine we only have one winding. We only care about the magnetic field which is perpendicular to the winding's closed surface. The sum of that magnetic field is called the magnetic flux. When the winding and the magnet are aligned, the magnetic flux is at its maximum, right? The magnetic field is completely perpendicular to the closed surface the winding creates. Once we start spinning the rotor, we see that the magnetic flux decreases until we reach a minimum when the magnetic field is parallel to the winding and is barely passing through it. So why do we care about the magnetic flux? Well, we care about it because of Faraday's law of inductance. It states that the voltage in a closed loop will be equal to the rate of change of the magnetic flux in that closed loop. The closed loop in this case is the winding. You probably know the famous quickly move a magnet through a coil of wire connected to a light bulb experiment. The magnet has a magnetic field around it, and the flux passing through the coil of wire changes as we move the magnet in and out. The faster we move the magnet, the greater the change in flux, and according to Faraday's law of induction, the greater the induced voltage. So if I rotated a DC motor like this, a quick acceleration followed by a deceleration, what would you expect the measured voltage waveform to look like? Take a second to think about this. I don't know what you answered, but correct. It would look like this. A large spike in the beginning, since the rate of change of magnetic flux is increasing, followed by a negative voltage, because the rate of change of magnetic flux is decreasing. And the amplitude is simply due to how quickly the rotor was spinning in each scenario. Now let's assume we rotated the motor at a constant speed. What do you think the waveform would look like then? DC? AC? Would there be any ripples? If so, why? Correct again. We would get a DC voltage with ripples. To see a section of constant speed, I'm just going to set a trigger and zoom in on the timescale. Each winding experiences a different change in magnetic flux, so every time we change between windings, there's a small ripple in the voltage waveform. If, for example, we increase the number of segments in the commutator, we would increase the voltage ripple frequency, but decrease its amplitude. The LEDs I have a forward voltage of around 1.8 volts, so they need around that voltage to emit light. So with the motor I just showed you, which I had lying around, it was pretty close. With 500 millivolts per division, it reaches just a little under 2 volts. I chose a resistor to make sure the current on the LED wouldn't exceed the LED's max current and tested it out. We can see it's lighting up a bit, but not as much as I want for this project. To overcome this issue, I needed to spin the motor faster. So I figured a simple solution for this would be to order a similar motor with a gear. That way, with a bit more torque, I'll be able to get much more voltage out of it. Spinning the motor after the wind turbine blades are installed will be quite easy, so the added torque is not a problem. And this is the result. With 5 volts per division, I'm reaching around 13 volts. I again put a suitable resistor to see how well the LED would light up. This is just right. I could put capacitors to help the light last longer, but the only capacitors I have that are big enough to make any noticeable difference are electrolytic, and they're polarized, so it's better not to have any significant voltage difference on their negative side, and if the rotor is spun in the wrong direction, it might destroy the capacitor. Okay, that's it for the generator part. Let's take a look at the 3D printed parts. Here's the turbine. I modeled it in FreeCAD. It's composed of a turbine stand, a middle hub, blades, and a dome. It all started with the blades. I looked online for wind turbine blade design and found this. So I looked for the airfoils, found only a few, and improvised. Pretty much making sure it looked legit and that the blade tips weren't too thin so I wouldn't have any issues with printing them. I used the macro to import the airfoils and created a loft between them. Next up was the middle hub. It's connected to the blades, the motor, and the dome to cover up the front. I like this cutout. A friend gave me the idea. It's super simple and it lets me connect the rotor to the hub really well without any fasteners. The blades go here and are fixed in place with simple dowels. I also thought for quite a while how to connect the dome to the hub. until I thought of this groove. It's a bit difficult to put the dome in place, but once it's in, it moves around really smoothly. Here's the dome. You can see the counter groove here. And finally, the wind turbine stand, which holds the DC motor. The bore is the exact diameter of the motor, and I used an M3 screw to tighten it in place. And here are the holes to allow the resistor and LED to pass through. And the reason for this entire build is because my brother works in the renewable energy industry, and I think a tabletop wind turbine is a must for him. Alright, that's it for this video. Thanks for watching, and see you next time.